All right, so sometimes factor by grouping doesn't work. We are going to go through something called the rational root theorem. The goal is to find numbers that could potentially work to start factoring a polynomial of a degree of 3 or higher, and we'll use synthetic division to do that. The possible numbers that are going to work are going to come from the leading coefficient and the constant at the end, and it's a ratio of the two and their factors. That sounds a little complicated, but it's not too bad. So we basically take the factors of the constant term at the very end, so like in this example 3, which is only made up of 3 and 1, but also the positive and the negative versions. And we divide them by all the possible factors of the leading coefficient. Like for this one, the leading coefficient is 6, so we could be dividing by 6, 3, 2, or 1. Those are all the factors of 6. So here you see they split up into a bunch of fractions. So let's get into an example of this. We'll start simple. So here, my constant term is 20, and my leading coefficient is 1. So we're dividing by 1, so it's actually just the factors of 20. All right, so we have 20, 10, 5, 4, 2, and 1. What we're going to do is we're going to use synthetic division and try out any of these random numbers. And the goal is to get 0 remainder so that we can figure out if it went in evenly. In this case, I'll try and I'll fail. So I know 10 doesn't work. So maybe I'll try another number. So I'm going to try one more time. I think we'll try 1. It gets a little cut off the screen here, but 1 ultimately doesn't work. So it's a little bit of a fishing game to figure out what one works. But since neither of them had a remainder of 0, we say neither worked. Eventually, we find ourselves at a spot where we can find one that does work. So I tried 4 here. I do synthetic division, a lot of adding, a lot of multiplying. And in the end, I get a remainder of 0. That means it works. Now remember, that's one factor, and the other one is x minus 4, since 4 was the solution. Now, at this point, I'm going to have to factor again, and this one factor is just like a normal trinomial, and I get my 3 factors, which also gives me my 3 solutions. All right, so this is a little bit of a longer one. We're going to end up doing it twice, but the concept's still the same. So what I'm doing here is I'm figuring out my possible numbers to start dividing this by. So I take my factors of 12 and divide it by the factors of 2. So notice I take 12 divided by 1 and 2. I take the next factor of 12 and I divide it, which is 6, divided by 1 and 2. And I continue on with all the factors of 12 divided by all the factors of 2, which are just 1 and 2. You might notice that some of these are actually kind of repeats. So like, for example, 12 over 2 is the same as 6 over 1. So we don't need to do the same thing twice. So I'm just going to cross out all the ones that are equal to each other. And this will give me a truncated list that's perfect to use. And it's still going to be a little bit of work. It's a little frustrating. So I've listed out all my factors. Don't forget that's actually both positive and negative of all those numbers. And I'm going to jump right in. I'm going to try a factor. And I actually nailed it on the first time here, I believe. So let's see. I'm starting to use synthetic division. I'm hoping for a remainder of 0. Oh, wait, nope, didn't get it. So 4 doesn't work. So I try again. All right, let's see what we get. We set it all up. We try 3. And you might do this. Again, there are about 16 possible roots here that I'm going to use. Hopefully some of them come up twice, or not twice. Hopefully more than one works. So in this case, 3 works. So I say x minus 3, since the solution was 3, the factor would be x minus 3. And I look here, factor by grouping doesn't work. So I have to do it again. But luckily, we can use the same roots that we had. Actually, we have less roots to choose from since we're only doing the factors of 4 over the factors of 2. So I can just cross out everything that's less than 4. And at this point, I try, and now some of these numbers are weird. You might get something like the fraction that'll work. And in this case, I only had 6 left, but I'll try the fraction of negative 1/2, and it does in fact work. So I'm going to rewrite out my new polynomial in its factored form, And hopefully we'll see if we can factor more, but we do have alternatives if we can't. So I took out the greatest common factor. I'll rewrite this a little bit bigger in just one moment. So here is my factored polynomial. We have x minus 3 from the 3 working in the original, x plus 1/2 from the negative 1/2 working, and this was the remainder with the 2 factored out just to make it a little simpler. So my x squared minus x minus 4 doesn't factor. So what I'm going to end up doing to solve this is using the quadratic formula. It's a little bit tedious, but we'll know how to do that. So we'll plug in all those numbers and we'll simplify. So now we have all of my roots, 4 roots here. All right, we are going to write a polynomial with the least degree, with the leading coefficient of 1, and the roots 3 and 2 plus root 5. That sounds way more complicated than it is. We're basically saying, hey, those are the solutions. What factors give us those solutions? And really, we just do x minus whatever they gave us. Now, we do have to be careful. Anytime we get a root, we actually have a secret buddy that accompanies that root, and it's the opposite sign. So instead of 2 plus root 5, we also have a 2 root minus root 5. And we can distribute in that negative since we are subtracting that whole thing. Now, there is a fun way to simplify this. It gets a little complicated, a little hairy, but follow along and see if you can make sense of it. What we're going to do is we're going to group the x minus 2's together. And what that creates is a difference of squares pattern. So if you remember how the difference of squares factors, we can do kind of a shortcut to multiply this. We can call it x minus 2 squared minus root 5 squared, since that middle term will cancel out, since we have a plus and a minus. And that helps us simplify that a little quicker if we remember some properties about squaring binomials. And in this case, we're still just multiplying out and making sure we repeatedly distribute all the factors. There's several different ways to do it. It's a little tedious, and we'll go over that in class as well for anyone that has trouble with it. And here is my final polynomial. Combine up all the like terms, and boom, we did it. Almost. Hold on. There we go. Done.